Welcome back. Today we're looking at Laplace equation on a semicircular region. Last problem we looked at a full circular region with no boundary conditions, right? Just had one condition for the whole circle, which you can consider a boundary condition or an initial condition. For this problem, you can see here we have a semicircle, so it's going to look like this. And it wants a solution on the inside of this region. Well, let me do it this way. It's asking us for this point here, so like this radius throughout here is what it wants. A solution for everywhere inside here is where it wants it. So I'm just going to draw it like this. That's what it wants. That's what it's asking for. It's saying r is less than a. A is the radius of the circle. So this is a. This is a. This is a, right? It should look more circular. Get the idea, because it's going to be same radius throughout. This is what we're solving for. Okay, so find a solution, u of r theta, just like before, in the semicircular region that satisfies the boundary conditions. So we're given 3 conditions this time. So that means for this time, the boundary value problem is going to be easier to solve. We don't have to worry about, theta being periodic. We don't have to do that weird thing we did last time up here. Where is it? Here it is. We had ensured that theta has to be periodic with 2 pi. That's the only way we were able to solve this boundary value problem with no boundary conditions. We just had to assume that each condition maintained periodicity, right? That's how we figure that one out. But for this one, we have actual conditions. Imagine it's like the rod from the heat equation, but it's bent. And on the ends we have, those are like our ends of the rod. It's just a bent rod, so we have these polar coordinates. So we're going to have theta for our boundary condition. We have theta of 0 is 0, and we have theta of pi is 0. Assuming u is single valued and bounded in the given region. This is just the semicircle, right? This is the ends. This is the semicircle itself from 0 to pi. Find the solution if f of theta is theta times pi minus theta. Okay, that's just giving us the, oh wait, we don't need that. Ignore that part. We're just going to ignore we're just going to assume it's f of theta. Okay, so step 1, separate variables. We already know how to do this from the last video. It's just, I'm just going to write the solution down. Alright, these are the 2 equations we were left with. Step 2, boundary value problem. We have these 2 conditions here. We're going to use the theta equation this time. So that's what we used last time, yeah. Yeah, same equation. Because remember, the region varies in theta. It's a circle. Think about it that way. So for this problem, we know from experience for a Dirichlet boundary condition for the case when lambda is less than 0. By the way, this is for the case when the separation constant is equal to positive lambda, in case you're wondering. That's how I use it for all of my videos here. So when lambda is less than 0, we know we end up with the case when we have positive minus mu, which is just going to be our e to the mu whatever plus c2 e to the negative mu. So then that's just going to be that's going to result in c1 or c2 whatever being equal to 0. One of them is equal to 0. And then you do the second boundary condition, and then you're left with that whole e term. And then in order for the e term to be 0, mu is 0. If mu is 0, lambda is going to be 0, which is less than 0, so then this doesn't work. Remember? So this is only trivial. And then remember from now we have the case when it is 0. Remember this is the reduction of orders case, when you're left with c1 plus c2 theta in this case. That would lead us to c1 being equal to 0 and c2 being equal to 0. So this is only trivial. Now, for the last case, this does lead us to something. This is the case that leads us to sine, if you remember correctly. I'll just define that there. We know that from solving the, let's see here, because it's plus, so it becomes negative. This is the complex case. Right, we solved this a million times already. So then big theta is c1 cosine mu theta plus c2 sine mu theta applying our first boundary condition. We get c1 is 0, right? So then we're left with theta equals c2 sine of mu theta, which is good, but then we have to do the second boundary condition, which was pi. Interesting. C2 sine mu pi. So for this case, remember we want this to be equal to 0. We'll make sine equal to 0, anything of n pi. Sine of n pi would be 0, so we're going to set this equal to n pi. Solve for mu. Oh, that's just n, isn't it? These cancel. Wow, look at that. So our h sub n for this case, remember just because it's for any n, right? Sine of n theta, little theta, right? And then what would our lambda sub n be? Our eigenvalue. Eigenvalue would be, it's just mu squared, so n squared. Eigenvalue, eigenfunction, there we have it, step 3. Remember last time this was also a little bit tricky last time. It's the same process, I think. We'll solve for r. Remember we're going to define, this is a Euler equation, so if we go back up here, I'm just going to copy what's up here to be honest, because we already did it. Where is it? But the end is going to change though, so I don't want to copy the whole thing. Here it is. Yes, I'm going to go down to here. So you should know how to do Euler equations. This is from second order ODEs. I guess I'll move it all over to this page. Okay. When you propose r equals r to the whatever, I chose h. And then you just plug those in, simplify down, and you solve for lambda, right? Well, no, you don't solve for lambda, but you reduce it down to this. Let me get my pointer. You reduce it down to this. We know from before, well, this is this one case. Oh wow, it works the same as before. This is the case that we have here. This and this, right? So we know if this is equal to this, then h squared is equal to n squared. So then if we take the square root, we're left with this. So then r can be rewritten as this. Right, this is for an Euler equation. This is the general solution for an Euler equation. So now, before, if you remember last problem, we were on the inside of the circle. So let me write this out. Last problem, it asked for the outside of the circle for a solution on outside of, well, I'll just call it the region. And in that case, what we wanted was a bounded value as r went to infinity. So if we look back up here at our work, you see as r for this term right here, sorry, it's kind of all over the place for this term, which is this one right here, as r went to infinity, this whole term approaches 0, which is a definite value, so it's bounded. All right, so that value is bounded. If we look at this one over here, which is right here, as r goes to infinity, as n increases, this whole term is going to go to infinity, right? So you can see that that's going to be unbounded, so we remove that term. We don't want it. We only want this term. For this problem, let me just write this out. We wanted r to go to infinity. As n increased, we wanted r to go to infinity. So was unbounded. For this problem, we want the solution on the inside of the region. What point on the inside of the region, we're talking about radius, is do we have a definite value? 0, right? If the radius is 0, we know what that is. So we can just say u must be bounded when r equals 0. So that tells us if r is 0, yes, so if r is 0, you can look up here. I'm just going to copy this down. This term, I'm going to write it like this. This term goes to 0, right? Because, well, it's not, it doesn't go to 0, but it's undefined. This term is undefined when r equals 0, right? Because you divide by 0. So this is all we're left with. So we get rid of this. Sorry. Get rid of this. This is what we're left with. R is equal to a sub n, r sub n. R, not sub n, but to the n. Okay. So now we have our r sub n. We're almost done. I need another page. Okay. For step 4, fundamental set of solutions and the general solution. You know what, I'm just gonna skip right to the general solution. We know how to do the fundamental set of solutions by now. So for the general solution, I'm just gonna, here, I'll write it out really quick. It's only one step. Remember, we can find a fundamental set of solutions. It's just the multiplied versions of this. So it's a sub n, r sub n, times, I think it was c sub n, sine of n pi. And then this is going to become a sub n. Well, I'm going to call it a new constant. I'm just going to call it c sub n. This is their new constant. Different from c sub n, different from a sub n. Even though it looks the same as this one, it's different. I just prefer to keep it as c sub n times r sub n times sine of n pi. That should be n theta. That should be n theta. Yeah, that's n theta. Whoops. That would have been 0 if it wasn't. Okay. Step 5. Fourier series, right? So we have one case left. We can kind of treat it as it's kind of on a circular region. This is kind of considered the boundary. The semicircular region is kind of considered the boundary. But you kind of treat it as the initial condition. Like think about the center of the rod. Like you think about the rod, the inside of it, that was the initial condition, the temperature distribution. For this case, you can kind of think of it the same way. So we're going to have UA theta is equal to F of theta, which is this, we're just going to write this as a sum, C sub n, A sub it. Oh, yes, I'm plugging in, I was following my notes there. I'm plugging in A in for R. So it's A to the n. Where was I? It's sine of n pi and theta. So then from this case, this is our answer. What would C sub n be? C sub n would just be, we have this A sub n here, so it's going to be 2 over the length, or the radii, not the radius, but the length of the rod. Well, the length of the rod in this case would be pi, right? Because theta goes from 0 to pi. So it'd be 2 over pi. Now we also have this A sub n term here. So C sub n gets multiplied by the A sub n term. So I'm just going to go ahead and move it over to here. So A sub n, A to the n, sorry. The integral, remember 0 to pi, I multiplied it by 2 already. F of theta times sine of n theta, d theta. And that's the answer. So a pretty simple problem compared to the last one, right? Semicircular region is a lot easier than the full circular region. I have one more example problem. It is I have it right down here. It's a full circle with a Newman boundary condition. So it'll be similar to the first example we did. Okay, so this was example 2. Hope you enjoyed, and I'll see you in the next video.